Welcome to the Computer Networks Laboratory Session number 2. From now on, I will go ahead and call this course as Socket Programming in C. Today what we will be covering is protocols, socket creation, and data transmission. But before starting the second session, we will be covering the leftover parts of the laboratory number 1, where we stopped at the opening and closing and writing into files. Alright, let's get going. It's 39 and let's go. So, what is file? So first, before going and starting to create sockets, we have to understand what files are first, because they're very similar to sockets. Let's try to understand what is the similarity. So Linux works with streams, meaning Linux is based on low-level file input-output and socket input-output functions that make up what streams are. So let's just, I will give a simple example where we have a standard input and standard output, and if you have previously studied C or C++ programming, you might have created a Hello World program where you printed out Hello World text on a standard output by calling cout Hello World. That meant you were giving the string of Hello World to the standard output stream. So what you were doing is you were working with streams. So that stream is inside Linux referred to as file descriptor. And as you can see here, when you were printing out that hello world text, what you were doing is you were providing that text hello world to the file descriptor 1. At least that's how Linux was understanding. So when two developers explain each other how to give the hello world text to the standard output, when they program, the Linux understands the developer not as like printing out that text on the standard output, but instead the Linux understands it as giving the hello world string to the file descriptor 1, and that is in English referred to as printing out hello world on standard output. And in Linux, not just in Linux, in any operating system, that is referred to as giving the string hello world to the file descriptor 1. And the standard input is the actual keyboard input that the user types in data with, and that is actually received from the file descriptor of 0. And now we can make an assumption that file descriptor is basically a number that represents a unique stream. And whenever we work with files and sockets, what we will be doing is we will keep on continuing to create the list of file descriptors, increasing the list of descriptors, start creating the stream number 3, which will be, for example, our file, or stream number 3 that will be our socket, and then we will create a file descriptor number 4, 5, 6, 7, so on and so forth. So what we will be doing is we will be creating file descriptors when we work with files or sockets or any kind of other socket or any kind of other stream. So files and sockets are referred to as streams. So now we have a basic understanding of how Linux works with files and sockets. Let's try to understand more what the file descriptors are. So this is a formal definition of what the file descriptors are. Operating system files are created and sockets simply as numbers to be able to easily distinguish them. And low-level file input and output functions require file descriptor for the purpose of making input-output operations. So the input-output operations is basically writing and reading from the input-output streams. The input stream is where you read the data from, and the output stream is where you write the data to. So here, as you can see, this standard input and standard output is a perfect example of the input and output streams. So the standard input is the keyboard and standard output is the console. And the next input-output streams could be your files. For example, you might want to read data from a file. That would be your next input stream. And then if you want to write, create a new file and then write into it, that will be a next type of output stream. And streams are the same thing. So what you will do is you'll open a socket and you might read from that socket using an input stream, or you can write to that socket. So that's how you can understand the similarity between sockets and files. All right, both socket and file have input and output streams, and sockets are a little bit more advanced than files. I hope I'll explain it a little bit later. And socket descriptors can be used simply as file descriptors as well. So you don't have to worry about differentiating between files and sockets actually, because while programming they're quite similar. You just open a file and then start writing data into it, and exactly the same way you just open a socket and start writing to it. So there's a big similarity between the two. So the next step is actually opening the file. So let's try to take a look at the function calls that we need to make to open a file, and then the function call that we need to close that file. Actually, whenever we work with streams, meaning sockets or files, we have to first open, and after opening we have to make sure to close that stream. Because there could be problems if you don't close the stream. For example, if it's a socket, then the other end could be waiting for messages from you if you don't close it. Or if it's a file, then the change that you made to that file could not have been saved. And if you call that close, all the modifications to the file will be applied with regard to files. Or if it's a socket, then the other end, the other company will also make sure to close that socket, because a socket has two ends, right? The two devices talk to each other, and then if one of them wants to terminate the connection, then it will call that close function call. And in here, what we're doing is we're taking a look at file opening and file closing. So in order to open a new file, I wouldn't say a new file. In order to open a file descriptor to a file, we have to make a function call that's called open, and it accepts two parameters, and the first of which the first is the path to the file, and then the second is a flag. Flag is simply the way of opening that file. For example, the table on the right side provides the values that we can provide to that flag. For example, the first one means creating a new file if it doesn't exist, or the trunk means if the file exists, then whatever the change that I'm going to make, for example, writing a new text, is going to be from the beginning of that file. The file might contain data already, but what I will do is I will overwrite the data from the beginning. All the data inside that file will be erased, and I will start writing from the beginning, from zero. And then we have the append, that is the alternative to the truncate. That means if the data already exists in that file, I will just keep on adding the content from the end of that file. And the next are read only, write only, or read and write. Okay, so once we open that file, like I told before, we have to close that file descriptor. And I want to make a note at this point. So when you make an open function call, what you can see here is that open function is returning an integer, and that integer is the file descriptor that was created for that file in that path. And whatever the change that we will be making, for example, erasing the data or writing content to that file, we will be making those changes using this file descriptor. And one usage of that file descriptor is just closing that file descriptor. So The close accepts just one parameter where we will be giving our file descriptor that we received from the open function call. Okay, let's go ahead and see one example. And okay, so this example provides us writing data into a file after opening and in between opening and closing, where we will be making the write function call that accepts three parameters. The first parameter is the file descriptor that we got from by making an open function call, and then we will be providing the data that needs to be written into that file. And then we have to specify the number of bytes. How many bytes of this buffer do I need to write to this file descriptor? That's basically how you can understand the write function call. So let's go ahead and see the example. I hope you can see it. It's a little bit small. The font size is a little bit small. I'll go ahead and increase the font size a little bit. So what we're doing in here is we are creating a file descriptor, the variable into which we will be storing the file descriptor, and we are creating a buffer that contains the text that we want to write into the file. And then what we're doing is we are opening that file. The file's name is data.txt with the flags of creating a file if it doesn't exist, and we want to say that we don't want to be reading, we only want to write it to the file. And then we're saying whatever the content is, whatever the whatever data that the data.txt file contains, I want to erase it and I want to start from the beginning. So after making a open function call, we have the value of file descriptor stored in this integer variable, and it's just fail-safe code. We're checking if the file was opened successfully, and then we are printing the content of the fd integer variable. We're just printing out the number, and that is the number that was assigned to that stream. The stream means the data.txt file, right? And then what we're doing is that we are trying to modify the content of that file by saying I want to change the content of this file descriptor, not the content of the file descriptor, the content of the file to which our file descriptor is pointing to, using the data inside this buffer. So basically what we're doing is I want to write this buffer into this data.txt file. So logically, after this line of code, what we need to see is whatever the content of the data.txt was, the content must have changed to let's go the string, basically. And then what we're doing is, as I told you before, we have opened a stream, a file, and then we have written and we made a lot of changes. So now is the time to close it because our process is closing, right? So now we're making sure that we are closing that file descriptor. That means the job is done. The file's content must have changed. And here on the right side, we can see an example when we are compiling the flow.open.c file that contains the source code, and then we are running the executable, and we're seeing that the file descriptor has a value of 3. And I want to make a little note here that that 3 was actually generated as the next file descriptor followed by the standard input output error, and then after we opened a new file, that file actually contained a file descriptor with a value of 3. So now we have a slight understanding of what the file descriptors are. And when we printed out the content of a file by this command cat, it's simply just printing out the content of the file, we saw that the content of the file was let's go, as we wanted it to change it to, right? And okay, we will not be just trying to understand the by the presentation. I will also share the source code that we can run here. So let's try to copy that source file and compile it and run it and see how it will change. And we'll do it as the previous time. So the source code is from the lab 1, and the low open.c file is right here. So let's copy these two files that are called data and low open files, and let's copy them. I am not sure why my computer is so slow. Okay, all right, copy it. Okay, and go ahead and open your C drive, CYGWin directory, home, and that Kevin will be different in your computer. It will be your username. And let's go ahead and paste our file here. Oh, oops, I apologize. I thought I copied it, but I didn't somehow. I will just go ahead and drag and drop. So that files are located here, so that I'm copying the data.txt file and lowopen.c file. And now what we'll be doing is let's just take a look at this content of that lowopen.c file. It's exactly the same code as we have just studied. It's creating a buffer, opening that data.txt file and writing a data to it, and before that printing out the file descriptor. So let's go ahead and compile that lowopen.c file and see if we have the exact same matching output. For that, what we will be doing is why did I close it? Okay, I will just make sure to open that directory on the left side so that we could see the content of the data file. And okay, before compiling and running, I want to show you that the content of this data file is like this. This is the content of the data.txt file, and we can even make changes into it. And remember that what we want to see is, after compiling and running that lowopen.c file, we want to see the change inside this txt file. It has to be let's go, the let's go string. It has to be here. And now let's close this file and compile and run it. That will be done by making this command gcc lowopen.c -o. Let's go ahead and call this executable open. Okay, so now we can see that we have just compiled that C file into an executable called open. So now let's call that program. So when we open that program, the output is exactly matching with the output. Oops, I apologize for this confusion. So this is where we were looking at. Okay, so the output was file descriptor 3, as we can see here. That means the file descriptor was continued after the standard input, output, and error. And now that this line of code has been executed, let's go was actually, this buffer was written, and that is why the program exited successfully by printing out this text. What we should see is the content of the file must have changed to let's go. So let's go ahead and open the data file. And now we can see that the content of the file has changed, right? That means we have successfully covered the file opening and closing and writing data into file. Okay, the next thing is reading the data stored in the file. So the first step was actually the output operation, that was writing, and now the next thing is input operation, that's storing, that's reading the data from the stored from the file, and that is done by making a function call called read, and that accepts exactly the same parameters as write. That accepts the file descriptor and the buffer where you want to load the data to. And the n bytes means the size of the buffer, so how much data can you store inside this buffer. And this is the example where we are reading the data to our buffer. Here you can see we're creating the buffer with a buffer size, and we'll take a look at the number, the value of this buffer size, and then we are opening the data.txt file with a flag called read only. And if the file does not exist, we will be having this open error text printed out, and then the application will stop. Otherwise, if the file exists, then we will have the file descriptor printed here, and then we will be reading the data from that file descriptor into our buffer. And then we will print out the content of the file as file data and semicolon and the string. And then we'll be closing that read-only file. And then here you can see that the content of the content of the buffer was let's go, and then that data came from the data.txt file. So now let's go ahead and compile and run that. And for that we have to copy that file into our directory. So the name of the source file was low read, and now what we have to do is we have to compile this low read.c file. For that we have to run exactly the same way as here. Low.read c file -o read. So now we have the read executable here. And now if you take a look at the read, it's also exactly matching with the inside what was inside the presentation slides. It's reading the content of the file to this buffer by making a read function call, and then printing out the data as file data semicolon string. Let's go ahead and run that read executable, and now we can see the output is file data let's go. And now let's change the content of this file and make sure that it's reading from the file instead of maybe not being fooled, because I might lie to you sometimes. I was just messing with it. I'm not going to lie. Okay, 1 2 3 4 5 6 7 8. Let's say we have just modified the content of that text to this string, and now let's go ahead and call the read executable again. And now we can see the content of the file is 1 2 3 4 5 6 7 8 2. And actually this weird character was because of the ending character. All the files must be ending with the end of file character, and we did not specify that here. Okay, now we're good to go, and the last step is file descriptors and sockets. So this one is the most important part, where the source file shows you what is the similarity between the files and the sockets. As you can see, we are creating three file descriptors, and for the file descriptor 1 we are creating a socket, and then for the file descriptor 2 we are actually opening a file, and then for the file descriptor 3 we are just creating another socket with different parameters, and the first one was TCP and the second was UDP. And we are printing out the file descriptors, and just what we want to see here is that the file descriptors must be in increasing order without overlapping each other. That means we must not have 0, 1, 2, 3 as a socket, 4 as a file descriptor, and then 4 again as a socket. That would mean like the file and sockets have nothing in common if the file descriptor of the file and then the socket were overlapping, like if they had the same value. But what we want to see is that they are unique. So here we can see the output of this exact code, and if you can see, we are compiling this source code and running, and we can see that the sequence of the file descriptors, the values of these file descriptors are 3, 4, and 5. That means they are different from each other. The files and the sockets are different from each other. The file descriptors are different. That means the Linux considers them as equal, the files and sockets. So for Linux it's just a stream. Socket and file is just a stream. That's why they have to be different from each other. Alright, let's go ahead. So here you can see this definition as well. Both socket and file descriptor are in the same number sequence. This confirms that the Linux input-output considers the sockets and files the same. Okay, let's go ahead and compile and run that source file as well, just to make sure that we're doing everything correctly, the right way. I apologize, it's not laboratory 2, it's laboratory 1. And this is the source file that we want to compile and run. That is called fd series. Okay, let's go ahead and I'm just clear out this because it's a lot of mess. Okay, gcc fd series dot output dash output and the let's say file descriptors. Oops, fd4 is undeclared. I apologize for the development issues. I think I might have made a little problem here. Okay, fd4. Oh, okay, it's a little bit customized. I will go ahead and create a variable for the fd4 too. I'm not sure why it wasn't created before, because here we're creating another socket as well. We have 3 sockets and 1 file. So it will give us fd1, 2, 3, and 4. But the issue was we didn't have fd4 here, and then it wasn't closed here. So let's go ahead and save it and then compile it again. So now we can see that the executable was generated from our source file. Now let's go ahead and execute that fds executable. And now we can see that the file descriptors are 3, 4, 5, 4. That gives me a little bit confusion, and I want to just check what is happening here. fd1, 2, 3, 4. File descriptor 1, 2, 3, 4. This is a little confusing. Alright. So the thing was, I apologize for the delay. I just missed this close fd2. After this close, the fd2 was actually released here. I don't know, like I just confused it because here is also fd2 was closed. I didn't expect it to be closed here too. Maybe this source file was modified after the first creation. But anyway, so the file descriptor 4 was actually released after closing file descriptor. So if we just get rid of this line, then what we will see is the sequence will be as we wanted it to. fd2, it is -1. That is very okay, that is also my bad, I apologize, because the problem was the stream was not actually created because we don't have that test.dat file existing. That's why the open could not actually open that file. So let's go ahead and create test.dat file. Alright, test.dat file. Okay, so let's just delete this. I think it was created after executing once. So now when we compile and run the source file, we will be seeing the correct output. Alright, so now let's go ahead and create test.dat file, and then go ahead and run our source file. So now we can see that the sequence of file descriptors are 3, 4, 5, 6, because we have our test.dat file here, and the fdseries.c file was able to open the test.dat file. And actually a little while ago, when the file was there, but this executable was returning -1. The reason was our program created that file, and actually the next execution did not have privileges to open that file successfully. That's why it was failing. And then when I deleted that source file and created a new file again, I copied and pasted that file again, it was a file with permissions given to any application. That's why now our application can open that file too. And now if we put that close function call here, if we call close fd2 here and get rid of this close here, what we will be seeing is we will have the 4 repeated again. That means the file descriptor 4 was released. And I hope that was clear, and I hope I didn't confuse you after this a little bit modified fd.series fd_series.c file. I wasn't expecting it to be modified from the PPT slide. So if it was without these lines and without this fd4 enclosing, just like in the presentation, it would have looked like this. So it would have looked like 3, 4, 5. Okay, let's go ahead and wrap up with the input and output file descriptors and continue with the lab number 2. So now what we will be covering during lab number 2 is the protocols, socket creation, and data transmission using those sockets. Okay, but before we jump into the lab session 2, I wanted to ask you guys if the sequence is correct from the lab number 1. And the first step is bind, the second is socket creation, the third is listening, the fourth is connecting, and the fifth is accepting. Go ahead and pause this video and try to think about if the sequence is correct. And now I will be continuing with the right sequence, which is, the first is socket creation, the second is binding, the third is listening, the fourth is accepting, and then the fifth is making a connection request. All right, let's go. So socket creation. So that's the goal that we're targeting for today, socket creation. So we have to understand what are the parameters for the socket function call that will be returning the socket file descriptor. So the 3 parameters are domain, type, and protocol. Let's go ahead and see the details. Protocol. The first element is protocol. So we have to understand what the protocols are. Network protocols are formal standard, which is like rules, compound of rules that devices use to communicate with each other. Whenever your phone tries to send the data to your computer, it has to follow the accepted protocols that can be TCP, UDP, ICMP, SNMP. There are a lot of protocols that are accepted for devices. And we have to use one of the protocols so that the 2 devices could understand each other. It could be compared to a deal, like let's say a deal between 2 people about communication for understanding each other. So it's like just deciding to speak on one language, not using a second language, so that the both parties communicate with each other using an agreed terms and conditions. So before we start transmitting data, we have to specify the protocol. That means it needs to be specified to create a socket. So now we know what the protocol is. Let's go ahead and see the socket domain. Actually, the protocol was right here, the 3rd parameter. And now we have to understand what the domain is. So the domain actually can have, I believe, 4 values, which are PF INET and PF INET6 and AF INET, AF INET6. What it represents is we have 2 different kinds of IP addresses, which are IP version 4 and IP version 6. It's actually IP version 6 is not completely implemented on all devices. That's why we're still using IP version 4. Which have, like, for example, the local IP address of a local host, which means the device itself, is 127.0.0.1, and that 127.0.0.1 is an IP address. And So you can take a look. Actually, there is no much difference between providing the socket domain to this parameter, providing PFINet and AFINet, and there is no much difference. But what the guides say is AF constants, like the if you provide PFINet, it will be anyway changed to AF by the um, compiler itself. So there is no much difference between providing PFINet and AFINet to the socket. So what basically everyone uses is PF or AFINet here. What they provide is this one. And if you want to use IP address 6 version, then go ahead and provide PFINet 6 or AFINet 6. It's totally up to you. And then the third argument is type, which is the socket type. So here, what we need to specify is the type of the socket that can be TCP, UDP, RAW, RDM, or SecPack, which are not needed to know because they are not really popular. And mostly use the two ones are TCP and UDP, which are transmission control protocol that contains two-way handshaking, and user datagram protocol that contains no connection establishment, which I will explain a little bit later. And what you need to understand in the difference between the two is the TCP is connection oriented, that means it's stable, and the UDP is connectionless, which means it's really fast. It doesn't have to establish connection. And you might be wondering, what does that mean? But whatever kind of protocol we use, we have to have a connection, right? So the TCP, what TCP does is, I better explain in the next example. So here you can see two images, and on the left side you can see that this person is slowly putting the products on the table, and that is rolling slowly with the correct sequence to the second person, and that is a really good example to TCPs. That means socket stream, and that means the sequence, the order of the packets are not ruined. The order will not be changing. The order of the packets will not be changed, and the person on the right side will make sure that the packets are being delivered to the person on the right side. But unlike in TCP and UDP, the packets order can be changed, and the sending company, the sending node will not make sure that the packets are being delivered to the and the destination node. That means the TCP is more reliable, as it will make sure that your packets are being delivered to your destination process in the right order, and the packets are being completely delivered, but the UDP does not make sure about that. That means it can be delivered to the destination node in any order, and it is not fail-safe. It will not make sure that your packets are delivered. But the UDP's advantage is it provides a faster speed, and that is actually UDP is highly implemented, highly exploited in games and videos and in streams, for example. But TCP is used in emails, let's say in messaging, in a lot. So both have their own unique usages. So let's go ahead and see what could be the other protocols. So the socket protocol, the third argument is can be an integer value, and the possible values you can find by just making this command line cat etc protocols. That is actually in any Linux-based device. By just making simple this function call, let's go ahead and make that function call. If you make this function call cat etc protocol, then you can see that 0 means IP, Internet Protocol, 1 means ICMP, Internet Control Message Protocol, and the 6 is the most, I apologize for the noise. Okay. So TCP means the transmission control protocol that we were referring to earlier as a reliable protocol. And right down here, 17, you can see it's UDP, User Datagram Protocol. These are all the values that you can provide to your socket creation, the socket function. And it can be TCP, UDP, ICMP, etc. As there are various subprotocols available for the machine, controlling information fetching, and so on. All right. So the three elements were the socket's domain, type, and protocol. The domain was PF or AF, INET, IPv4, IPv4, IP address v4, and then the type of the protocol, and then the protocol itself. All right. This is the last slide. One before the last slide, where we see that the data is being transmitted after creation of the socket, and we don't have to really understand it yet, because we will be working really hard on understanding the whole idea behind the socket creation and handling. But let's make a quick look over this source code. After creating socket, what we're doing is we are binding that socket to a server socket to the server address, and after binding we are listening to client sockets, and then we are accepting one client, and we have that client socket file descriptor stored in this variable, and then we are writing data to that client socket file descriptor, and then we are closing that client socket, and after that we are closing the server socket. And then here on the client side, the above code was actually the server, TCP server code, and below here is TCP client code. What TCP client code has to do is simply create that socket and then connect to that socket, right? And here you can see it's simple connect function call to that socket, where we specify the server address, and then after connecting to the server, we are reading whatever is incoming from the server socket. So the server is going to be writing the data to the client socket, and the client is going to be reading all the data and just printing out on the console, and and printing out at the end to the console. And here what we're doing is we are reading the data just like we were reading from a file. So we are reading from that socket file descriptor to our message buffer, and actually that message is a simple array, and we are reading every single byte until it finished. That means the read length will become 0, and while 0 means while false. That means the while loop will finish, and after the while loop will break and stop, and we will be seeing this message from server is the string that is our buffer, and then we will have this output function called count is this many times. That's actually the length of the string that was received from the server. That must match with the content of the message. I believe that must be somewhere above. Let's go ahead and compile and run that file, and then see the output ourselves. All right. So now what we need to do is we have to copy those two files, the TCP client and TCP server, to this folder in our C drive, CYGmin64 home. In my case, it's Kevin. And let's go ahead and do it. So the source codes are right here. So what I will do is I will just copy the two source files inside this directory, and then I will open up two terminals, one for TCP server and one for TCP client. Just like the previous time, just like in the lab number 1, here up above I will be running the server part, and down below I will be running the client part, TCP client part. So let's go ahead and compile the TCP server on the terminal above, gcc TCP server.c file, and down below let's go ahead and compile gcc client. Oops, I apologize, I didn't specify the output name. So that must have been followed by O, and let's give it the executable name called server, and oops, I forgot, I just lost my mouse. I don't know where it is. Okay, I found it. Okay, gcc tcp client.c and then -o client. Now we can see that we have the two executable files generated here. And before executing them, let's go ahead and open and see what is the content of the message, because we want to know what we are sending, right? And now we can see that the content of the buffer is actually just simply hello world. So the TCP server is going to be sending this hello world to our server by binding the server address, listening to client sockets, and accepting one client socket, storing the socket file descriptor inside this variable, and then writing the message that we created right here, and then closing the client and server sockets. So now that we understood what the server part is doing, let's take a look at the client part as well and just make sure that it's completely matching with the slides. So we're simply connecting to the server address, and then we are reading all the content, and we're just printing out the message that we received from the server, that which must be message from server hello world. Okay. Let's just now execute the TCP server and client and see the output ourselves. For that, we have to run the server. Oh, I apologize. We have to specify server, and then we have to give the port number, which will be, in my case, just 9876. And on the client side, we will specify the IP address of the server as well as its process number, its port number. And when we click enter, we will see that the server has finished execution and the client has received the message from the server that contained hello world. And then the number of bytes that were read were 13, which are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. That is the new line character, which is right here. It's not in end line, it's the end of the buffer. That's just \0 that's always there. Whenever you create a string, it will contain the end of the string character. That will be just by default \0. Okay, now we are good to go. I hope you understood and it was not a very complex session, and I hope to see you next week.